So how do we solve this? That's equal page 9, right? Yep. And what step I have? And this is what, step 5. Step 5. Now in step 5, apply boundary condition. First of all, we say that when y1 at x1 equals 0, there's no deflection. So this is nothing but just a support, right? If it's at the support, how do we know, how do we find the values? You just plug in this value into the first solution, which is this one. So we may want to call this, and just for the ease of discussion, let's call this equation 5 and this equation 6. Now we say apply this one in equation 5. We just plug in. What we know is plug everything into 0. And then you know that 0 equals A. Now cosine 0 is what?
1.
Yes. So that's A times 1. What is sine 0?
0.
Good. Plus B times 0. What is something times 0?
0.
0.
Of course, 0, right? You don't get anything if you multiply something by 0. That's one advice any mathematician will give you. So the special solution x1 is 0, so that means minus whatever you have here times, you can call it QC over PL times 0. Now from here, apparently this is gone. This is gone because they're all zeros, right? What do we have here? We found that A is actually 0, correct? Because A multiplied by 1 and that equals to 0. So we know here A is actually 0. So we found this. And similarly, the same idea, apply boundary condition at y2 and when x2 is 0, and this also have to be 0, and equation 6. And this would actually give us this result. If we do it that way, then 0 equals the same idea, right? Now you have C times 1 plus what? Plus D
Times 0.
times 0 and minus Q L minus C over P over L times 0. So here, here, right? So we also have C equals 0 from here. Now, in step 6, we know that when x1 equals L minus C, the deflection at x1 must be equal to the deflection at x2 when it's calculated from the opposite side. Because when x equals L minus C, that also means x2 equals C, correct? They are the same thing. Would you agree? if you go back to the original definition that we have, what is at this point? This point is, if you calculate x1, which is from point A, when x1 equals L minus C, x2 must be C. Is that clear? Okay.
Yep.
Yes.
All right. So we come back here, and we're going to use the same condition. That means what? That means if this is the case, the deflection must be the same. That means y1 when x1 equals L minus C must be y2 when x equals C. That's basically what I'm saying. Right? So what we're going to do is what? Is just plug everything in. And to form this deflection. So what we're going to do is to plug this one in here, and we'll finish probably another step, then we can call it a day. All right, so we're getting there. So if you plug it in, remember, we're going to plug Lx1 to be L minus C and x2 to be C. So we're basically using equations here, 5 and 6. We basically use them by substituting L minus C into x1, and you get expression of y1, and you substitute C into x2, and you get expression of y2. Then you relate these two. That makes sense? Okay. So that's why we're going to write the following expression. You can do the same, but you're going to get the same result. First, the left-hand side of the equation is coming from equation 5. And that is written like this. We don't know B, but we know B times sine K is K times L minus C. Now remember, we replace x1 with L minus C.
Professor, I just have a quick question. Sorry.
Yes.
In that first line on the far right, you have y1 equals x1, or sorry, y1 as x1 equals L minus C. And then you have that set equal to y2. Is that supposed to be all equal to each other?
Yes.
Okay, thank you.
Only at the point.
Okay, thank you.
Which is at the point when the force Q is applied. So at this point, the deflection must be the same. So our approach is to calculate deflection from the support A, from the support B, and reconnect them, combine them at the location where the force. So this is Q times C over P times L. Again, substitute L minus C into x1. So that becomes L minus C. Everything I did here, you can see this was the place where I use x1. So that is from equation 3. I'm sorry, equation 5. And then this must equal to D times this. Sine K L minus C minus tangent KL. Actually, I think I skipped one more step. So why don't I just go back? So I would explain to you why I get this result, but I skipped one step. So just plug in everything we know from before. Right? So here is D times sine K and times C. That was x2 minus Q times C minus K Q times not C, but it's L minus C, right? L minus C divided by P and L and times C. So this C and this C here, they were where the x2 used to be. So this kind of equation is what we call compatibility condition. The concept is very simple. Deflection must be compatible at the joints as long as the structure has no discontinuity. And discontinuity means the breaking of the structure. Okay, so I'm going to stop here. Of course, this is not the simplest example, but it's going to be one example that we will study maybe a month from now. But I want to show you that by using this example, you will take this opportunity to review several topics. So let's review this example. I hope you have fun because it's just mathematics. If starting from here, if you're lost from this moment equilibrium, please dig into your book piles, find out where the structural analysis textbook is. Take it out and find the topics on moment equilibrium. So that's one. And if you're lost about this is from mechanics of materials. How we relate internal moment to deflection and to slope. So this is the part where you need to get the books on mechanics of materials or strength of materials, I think. If you are lost here, it's not clear to you that how come we have two different parts? What is complete solution? If you have this question in mind, and that means you really need to find out your books on differential equations. All right, that's the purpose for me to introduce this. Of course, the examples from the chapter 1, buckling of columns, will not be that complicated. It actually will be much easier than this example. But I want you to take this example to review the materials that you may not be so familiar at this point. All right, and if you don't feel that comfortable about the examples that I did today, don't worry about it. This is probably a little bit more difficult than many examples I would solve in this class. However, in structural stability, what you're going to learn is how I solve all these different kind of examples and different problems. And that's why I mentioned at the earlier of the class, make sure you have a lot of papers and have a pen and learn how to take notes. Any questions before I let you go?
Yeah, can you just go over where you got the equations from equation 6 again?
How do I get equation 6?
On the first line, you kind of set some conditions that I'm confused about. The x1 equals, or the y1, x1 equals L minus C.
Is that here?
Yeah.
Okay, you mean step 6, right?
Yeah.
In step 6, what I'm saying is this.